L-BFGS is not just a sequence of random letters, but also represents a popular method for numerical optimization. Hello everyone, my name is Sal Balkus, and today I'll be discussing my research on the L-BFGS optimization method. Unconstrained optimization is the process of finding a minimum or maximum. It has many applications in industry problems. For example, to train a neural network, you need to be able to minimize the loss function. Nowadays, many businesses and governments work with big data sets that have many variables, and they might need to optimize a function of many variables. Gradient descent is a powerful tool for this. The idea is it's an iterative algorithm. You start with a point xk, pick a search direction pk and a scalar step length alpha k, and step to the next point xk plus 1. And this is done iteratively over and over again until a certain stopping criteria is reached, indicating that the optima has been found. Now, there's a lot of research on how to actually pick the search direction. One of the most popular methods is Newton's method, which is extremely fast. The way it works is you multiply the inverse of the Hessian, which is represented by BK here, and you multiply it by the gradient of the point that you're currently at. Now, this yields BK, and this is one of the fastest methods for finding an optima, but it requires computing the inverse Hessian, which, if you know a little bit of linear algebra, you know that finding an inverse isn't trivial, and it can actually take a really long time if the matrix is very large. That's why quasi-Newton methods were invented. The first quasi-Newton method was invented by W.C. Dabdon at Argonne National Lab. He was trying to run a Newton method optimization, but the program kept crashing before it could finish. So he decided to approximate the Hessian rather than computing it directly. This spawned a massive area of research into quasi-Newton methods, and eventually the Broyden-Fletcher-Goldfarb-Shannon algorithm, or BFGS, was developed, which has now become the most popular quasi-Newton method. The way it works is we first calculate SK, which represents the difference between the most recent point and the previous. Then we calculate YK, which is the difference between the gradient at the most recent point and the previous point. And then we use these to step to the next inverse Hessian approximation iteratively. So as you can see, we basically take the previous Hessian that we calculated and apply this formula to get the next one. And this is really useful because we don't have to compute the inverse of the Hessian directly, so it's faster. But at the same time, you still need to use the whole Hessian matrix, which if you have, say, 100 or 1,000 variables, it can take a long time to perform this matrix multiplication. The limited memory BFGS method seeks to resolve this problem. It too uses an approximate Hessian to calculate the search direction, but it only uses the m most recent iterations for the approximation. This is the algorithm here. I'll quickly summarize it. Basically, what you do is you take the gradient, use the m most recent sk and yk calculations to calculate this q, which then is used to calculate r. And this r represents the approximation of the search direction. So you basically iterate through, again, y and s, the m most recent y-ness, to get an eventual approximation where r is approximately equal to the inverse Hessian times the gradient. So this actually allows you to reduce the amount of storage that you need because you don't have to store the whole Hessian, and it can be faster because you don't have to multiply the whole Hessian. But this does lead rise to the question, how do we choose m? How do we decide how many variables sk and yk to store? So that's what our research question seeks to answer. We want to find a heuristic for calculating m. We also want to compare the L-BFGS method to Newton's method in BFGS for high-dimensional objective functions to see if this method actually allows it to run faster, or if it just allows it to, say, use less memory instead. That's what we'll seek to explore. To do this, we develop a numerical experiment. We implement Newton, BFGS, and the L-BFGS methods in MATLAB and evaluate them on a high-dimensional Rosenbrock function. This is the Rosenbrock function here on the right. We test the different values of m for the L-BFGS method to see how long it takes for the L-BFGS method to converge on this function. And then we also test Newton's and BFGS to compare their convergence speeds. The way we do this is we implement the methods as described and use a backtracking line search with the Wolf conditions to calculate the step length alpha. This ensures that the BFGS method and the L-BFGS method actually converge. We use the stopping criteria of the gradient-based stopping with epsilon equal to 10 to the negative 3, 10 to the negative 4, and 10 to the negative 5. We test all three of those. We also test the Rosenbrock function for of 100 variables and 1,000 variables to test the different orders of magnitude. Now let's take a look at the MATLAB code that we implemented. Here's the MATLAB code that we use for testing the L-BFGS algorithm. We start by setting our Wolf condition constants and the stopping criteria that we want to use, and we can change this depending on the test, as well as the number of variables in the Rosenbrock function. Then we run a number of tests, basically testing different numbers of m from m equals 4 up to m equals 64. And if we run this, eventually we'll start to see, it will output the time it takes and the number of steps that it takes. And then at the end, it will basically take everything that's been printed and output it as a matrix in a CSV file. Now these are basically define the Rosenbrock function and its gradient. This function defines the descent algorithm. Here we can specify the type of optimization that we want to use, and when we run it, it will give an output. And then we can see that this actually works. It prints, and it prints the time that the L-BFGS took for m equals 4 in the number of iterations. But back to this, we start by finding our variables, run the iteration, depending on which type of optimization we're using. It will calculate the search direction based on those formulas that we discussed earlier in the presentation. And then it will use the Wolf conditions. You'll use a backtracking line search to select the Wolf conditions as we discussed. And that's what this loop is all about, calculating alpha. Once we've calculated alpha, then we see that we can step to the next x value, decide whether or not we've met the stopping criteria, which can be based on several different criteria. And then if we have, we exit the loop. And if we haven't, then we keep going. This is a helper function for the Wolf conditions, and then this is for calculating the Hessian and Newton's method. And we can see that basically all these tests run, they print out in the command window, and they also, as I mentioned, go to the data. We also have this this plotting that basically this just plots the data and generates plots that I will show you imminently. Now let's look at the convergence speed. Here we see that for the 100 variable Rosenbrock function, for epsilon of 10 to the negative 4 or 10 to the negative 5, between m equals 4 and m equals 8, this is a log scale, we see this massive decrease in the amount of time taken by about 40% between these two values. And after that, it appears to somewhat level off and remain the same no matter what m is chosen. Now, for e equals 10 to the negative 3, there also is a slight decrease, but it continues to decrease slightly after that. But overall, there isn't a whole lot of change for the less strict epsilon value. For the Rosenbrock function of 1,000 variables, we see a similar pattern emerge. Again, for the more strict stopping criteria, we see that there's a large decrease in the time taken between m equals 4 and m equals 8. And then after m equals 8, it kind of oscillates up to m equals 256. Again, however, for the epsilon equals 10 to the negative 3, there's actually a little bit of an increase, and then it slowly decreases as m increases. So we see that generally the lowest values are for the higher values of m here. This data is shown here in this table. This is basically all the experimental data we took. And again, this is showing the same patterns. After m equals 4, it's pretty similar in time taken for the L-BFGS algorithm. And we also see that the iterations are virtually identical after the initial slow start of m equals 4. Now we'll go over to MATLAB for comparing L-BFGS to the Newton's method and the standard BFGS method. Here we are in MATLAB. This is the code for testing the BFGS and Newton's method against the L-BFGS method. It's very similar to the code that I showed previously, but we run the experiments with our new methods by specifying the name here and the function. And when we run them, it'll print out the time taken and the iterations for each experiment. We're basically running the same experiments as before with the new methods. And then eventually, once we get to the end, it will formulate this into a matrix and write that matrix to a CSV file so we can analyze the data. Otherwise, this function is basically the same as before. It uses the same methods and basically has the same code for the rest of the file. Now let's take a look at the comparison data, which is shown in this table. For the 100-dimensional Rosenbrock function, Newton's method was by far the fastest, both in terms of time and iterations taken. However, the L-BFGS method was faster than the BFGS method, especially for epsilon equals 10 to the negative 5, where it used far fewer iterations to converge. However, for the 1000-dimensional Rosenbrock function, we see that L-BFGS outperformed the other two methods significantly. In fact, for the epsilon equals 10 to the negative 5, it actually ran almost twice as fast as the Newton's method, even though it took 40 iterations compared to 7 for Newton's. This indicates that using cheap to compute iterations can be advantageous in some scenarios. In addition, the L-BFGS method used far fewer iterations than the BFGS method, even though it only uses the m most recent iterations to compute the Hessian or approximate the Hessian, as opposed to BFGS, which uses all of them. That brings us to our heuristic. So for our heuristic, we decided to choose m greater than or equal to 8. The reason that we did this is because our goal is to overcome this area of the graph, which is where all the poor performance happens, and reach this plateau where there's not really much difference between the values of m. Basically here, we see very large decreases in the amount of time taken as for each m up to this point, m equals 8. But for cases where this doesn't necessarily occur, like for epsilon equals 10 to the negative 3rd, you can consider m up to 13% to 32% of the total variables in order to reach this very optimal region, even though this doesn't really change that much here. Basically, the goal is to reach the speed plateau. Now, for a comparison, we found that L-BFGS always outperformed BFGS, which indicates that using only the m most recent iterations is actually more effective than using every step. Thus, L-BFGS is probably always going to outperform BFGS in most cases. L-BFGS also outperformed Newton's method, but only for the case of 1000 variables. This indicates that L-BFGS is best when the order of magnitudes of variables is roughly 1000 rather than in the hundreds range. Now, the limitations of our research, we only tested the Rosenbrock function. It would be a good idea to consider functions with different challenges, such as the Rastrogen function on the right here, which has many local minima. This would allow us to get a sense of what kind of functions the L-BFGS method works best on. We also only tested the Newton and quasi-Newton methods. It would be a good idea to, when we use other functions, to also compare different methods, such as Nelder-Mead, which doesn't even require any derivative information, in order to figure out what sort of conditions L-BFGS works best in compared to other methods that are maybe a little bit more exotic than Newton's and don't require the Hessian. So, to conclude, we decided on a heuristic. Choose m greater than or equal to 8 in order to reach the speed plateau. We observed that the best strategy for quasi-Newton's methods was to use only the recent curvature information to approximate the inverse Hessian. Thus, we found that L-BFGS is the clear choice for optimizing very high dimension functions. Here are my sources. Thank you so much for listening, and I hope that I was able to adequately inform your future optimization strategies. Thank you.